This video tutorial is straightforward. We'll be working through some example problems using the special trig limit. Let's find the limit of sine of 5x over x as x goes to 0. Attempting to evaluate directly, we get the indeterminate form 0 over 0. We will use our special trig limit to try to resolve this limit. A note of caution is required here. We will be using the argument that as x goes to 0, the function inside of the sine goes to 0 as well, so that sine of the function divided by the function will go to 0 by our special trig limit. However, note that the function in the denominator has to match exactly the function inside of the sine. In our problem, the function inside of the sine is 5x. But the denominator doesn't match that exactly. We're missing a factor of 5 in the denominator. We can remedy this situation by that old algebra trick of multiplying by 1. Rewrite 1 in the form of 5 divided by 5. Rearrange. Bring the 5 in the numerator in front of the limit statement. And this is justified by the fact that 5 is a constant, so it doesn't care what x does, it just remains 5. It's unaffected by the limit. And so even though at this point you probably see that by the special trig limit we get 5 times 1, I'll be a little bit more careful. Let u equal to 5x, and then reason or observe that as x goes to 0, 5 times x, or u, goes to 0. Replace 5x with u in the limit statement, and now use the special trig limit. So the limit is 5 times 1, or just 5. The moral of the simple example is that the function in the denominator has to match exactly the function inside of the sine before using the special trig limit. For this example, let's find the limit of x divided by sine of x as x goes to 0. This is the reciprocal of what we're used to. Here, the answer is obviously 1, so we're done. Just joking. However, this is pretty simple. We'll use the algebra trick that any non-zero number can be rewritten as 1 over its reciprocal. For example, 2/3 can be written as 1 over 3/2, or 1/2 can be written as 1 over 2. So we rewrite x over sine x as 1 over sine x over x. The numerator is unfazed by what x is doing, it's a constant, so we just have to worry about finding the limit of the denominator. And by our special trig limit, the denominator goes to 1 at the limit. So our limit is 1. The takeaway from this problem is that not only the limit of sine u over u is 1 as u goes to 0, but also the limit of u over sine u is 1. So we can always keep that in our back pocket. Now let's compute the limit as x goes to 0 of 1 minus x divided by x squared. Before we do anything else, let's check whether this limit can be evaluated directly. And indeed it cannot be. We get the indeterminate form 0 divided by 0. Also, at first glance, it doesn't seem like we can use our special trig limit since we don't see a sign anywhere. I'll give you a hint on how we can proceed. The hint is the Pythagorean trig identity. Sine squared of x plus cosine squared of x is equal to 1. Do you see how this is related to this problem? Maybe you want to take a pause and try to think about it. Subtracting cosine squared from both sides, we see that sine squared is equal to 1 minus cosine squared. And we can think of that as a difference of two squares, 1 squared minus cosine squared. So we could factor. Yeah, a difference of two squares is the product of conjugates. So we can introduce a sine squared into our limit problem by multiplying the top and bottom by 1 plus cosine x. We expand, use the fact that 1 minus cosine squared equals sine squared, do a little algebraic housekeeping, compute the limit of each factor individually, bring the limit statement inside the squared So find the limit and then square, and you can your professors will justify that later. Use our special trig limit. Find the limit of the second factor by evaluating directly. And we get 1 times 1/2. So our limit is 1/2. Perhaps one lesson we can take away from this is that you not only multiply by conjugates to get rid of the square roots often, sometimes you multiply by conjugates so as to introduce a trig identity, like the Pythagorean trig identity. Let's consider the limit as x goes to 9 of x minus 9 divided by the sine of the square root of x minus 3. Trying to evaluate this limit directly, we get the indeterminate form 0 divided by 0. We'll need to take advantage of the fact that since x is positive as x is approaching 9, x can be written as the square root of x squared. Remember, we can only take square roots of non-negative numbers. Rewrite the numerator as the difference of two squares, square root of x squared minus 3 squared. This will allow us to factor the numerator into a product of conjugates. Rearrange and compute the limit of the factors separately. The limit of the second factor can be evaluated directly to get 6. And we'll use our special trig limit to find the limit of the first factor. Let u equal the square root of x minus 3, and reason that u goes to 0 as x goes to 9. Now we can use our special trig limit, and we see that our limit is equal to 1 times 6. Sometimes completing a problem in calculus is really all about seeing the algebra. In the next block of videos of this camp, we'll be looking at functions which might not behave as well near a point. So I'm looking at these two functions as prototypes, absolute value of x divided by x and 1 over x. Try graphing these if you haven't seen these before, and in your own words, try to describe their behavior as x approaches 0. See what kind of problems you would run into if you try to compute the limit as x goes to 0 for these functions. See you next time.